Across dark wartime oceans, early sonar screens sometimes drew a second seabed where no charted bottom existed. If you watched through the night, that phantom floor could rise hundreds of meters toward the surface. By morning, it often sank again, moving with a regularity that rock and sediment could never possess. Operators first faced an unsettling choice between faulty instruments, strange water layers, and something alive. The echo stretched across enormous distances, too broad to resemble a ship, whale, or compact school. Sound pulses descended, struck countless tiny reflectors, and returned as a continuous band beneath the vessel. The band looked solid enough to measure, yet nets sometimes passed through it, with surprisingly little catch. Its daily migration deepened the puzzle because the apparent bottom responded to sunset and sunrise. No single animal seemed capable of raising an acoustic horizon across an entire ocean basin. The mystery, therefore, belonged not to one creature, but to a hidden community acting on a planetary schedule. Early interpretations ranged from temperature boundaries to suspended particles and vast aggregations of marine life. Some explanations addressed part of the signal, but none initially accounted for every depth and nightly movement. The false seabed became known as the deep scattering layer, a name describing an echo rather than a cause. That distinction matters because an acoustic layer is an observation, while its biological composition requires independent evidence. The investigation begins with a moving line of sound and asks what makes an ocean appear solid. Sonar works by timing echoes from transmitted sound, with stronger returns produced by sharper changes in acoustic properties. Fish bodies differ little from seawater, but gas-filled swim bladders can reflect sound with remarkable efficiency. Small crustaceans, gelatinous animals, and squid also scatter sound through tissues, shells, or internal gas structures. No universal species creates the layer because its membership changes with region, season, depth, and sonar frequency. Lanternfishes in the family Myctophidae are major contributors across many open ocean environments. Many bristlemouths, including cyclothone species, are extraordinarily abundant, though their acoustic importance varies with anatomy. Krill, copepods, siphonophores, shrimps, and small squid can strengthen or complicate the returning signal. Collectively, these animals occupy the mesopelagic zone, broadly extending from about 200 to 1,000 meters. Sunlight fades rapidly there, leaving dim blue traces above and near total darkness below. During daylight, many residents remain deep, where limited illumination makes visual detection by predators more difficult. At dusk, falling light becomes a cue, and countless animals begin swimming upward towards surface food. Imagine descending beside them, and you would cross streams of bodies separated by size, speed, and preferred depth. Near dawn, increasing light reverses the movement, sending many migrants downward before surface hunters regain their advantage. This diel vertical migration is directly documented, although not every layer member migrates, and not every migrant travels equally far. Zooplankton nets recovered likely scatterers, but avoidance, fragile bodies, and uneven sampling made catches incomplete. Acoustic measurements revealed migration continuously, yet echo strength alone could not identify every organism's responsible. Scientists combined nets, multiple sound frequencies, and direct observations to connect particular body types with particular echoes. Different frequencies respond differently to animal size and structure, helping separate some fish-dominated layers from smaller zooplankton. Even this approach remains interpretive because many species overlap and orientation changes their acoustic reflectivity. A fish tilting during ascent may return a different echo without changing its abundance at all. Gas volume can also shift under pressure, changing how a swim bladder resonates as the animal changes depth. The verified picture is therefore dynamic, with behavior and physics shaping the layer together. What fooled early sonar was not a stationary substance, but the combined acoustic presence of immense mobile communities. One explanation proposed that temperature or salinity boundaries alone produced the false bottom. Such boundaries can bend sound paths or create weak reflections, so the proposal was physically reasonable. However, a water boundary cannot readily explain nets catching migrants within the echo or animals rising after sunset. Another explanation invoked bubbles, which are powerful scatterers and can form biological or physical layers. Some siphonophores contain gas floats, and certain fish carry gas, but free bubbles cannot explain every oceanic case. The biological interpretation gained strength when echo bands moved alongside captured organisms on repeated nightly cycles. Still, calling the entire layer biological does not identify which animals dominate a particular return. An intense echo may represent relatively few efficient gas-bearing fish, rather than a greater mass of weak scatterers. Conversely, abundant gelatinous animals may contribute less acoustic energy than their ecological importance would suggest. Sonar, therefore, maps reflectivity, not biomass, species diversity, or feeding activity without additional constraints. This limitation prevents a bright band from becoming automatic proof of a dense fish population. Predator behavior supplies another test because tuna, dolphins, and larger squid often track vertically migrating prey. When prey ascend after dusk, predators may follow, feed, and descend, linking acoustic movement with observed ecological interactions. Yet, predator presence cannot prove the identity of every scattering animal, since hunters may target only selected members. Moonlight provides a natural experiment by changing perceived predation risk near the surface. On brighter nights, some migrants remain deeper or delay ascent, producing measurable changes in layer position. Cloud cover and water clarity can modify that response, showing that light intensity matters more than a simple clock. Oxygen also sets boundaries where low concentrations restrict animals, unable to tolerate prolonged physiological stress. Species adapted to oxygen minimum zones may hide there from predators, then leave when feeding rewards outweigh the costs. Temperature shapes metabolism, so crossing sharp gradients can increase energetic demand during an already strenuous migration. Food availability complicates every rule because a poor surface bloom may not justify the journey for all individuals. These interacting cues explain why the layer sometimes divides into several bands rather than moving as one sheet. They also warn against treating migration depth as a fixed characteristic of an entire species. Direct observation confirms repeated movement. Mainstream interpretation attributes much of it to feeding and predator avoidance. The balance between those pressures is tested by patterns, experiments, and models not witnessed inside every animal. Unknowns remain greatest where delicate organisms evade nets and darkness limits visual records. The layer matters because its nightly ascent transports carbon, nutrients, and energy through the water column. Migrants eat near the surface, then respire, excrete, or become prey at depth, carrying surface production downward. This active transport complements sinking particles and can move material faster than passive marine snow. When a lanternfish rises to feed on zooplankton, stores carbon and descends, its behavior connects two distant habitats. If a predator captures that fish below, the transferred energy remains within deeper food webs. If you remove the migration from an ecosystem model, carbon pathways and predator distributions can change substantially. The animals also consume and repackage particles, altering the size and sinking speed of waste. Their abundance makes them tempting fishery targets. But acoustic brightness alone cannot establish sustainable harvest levels. Many mesopelagic species grow slowly, occupy broad ranges, or remain poorly studied despite their apparent numbers. Removing large quantities could affect seabirds, tunas, marine mammals, and deep predators linked through food webs. Climate change may shift oxygen, temperature, stratification, and productivity, moving layers into new depth ranges. Warmer surface water can increase the metabolic cost of ascent, while stronger stratification changes nutrient supply above. Expanding low oxygen zones may compress habitat for sensitive species and favor animals with specialized tolerances. Such shifts could alter carbon transport, although direction and magnitude will differ among regions. Naval and research sonar must also distinguish biological scattering from seabed, submarines, and physical ocean structure. Modern instruments resolve layers far better than early systems, but interpretation still depends on frequency and context. The original mistake became useful because the false bottom revealed life beyond the reach of ordinary daylight. It showed that a seemingly empty depth could contain one of Earth's largest synchronized animal movements. The layer is therefore both an acoustic phenomenon and an ecological corridor connecting surface meals with deep respiration. Its changing shape records decisions made by millions of animals responding to light, hunger, predators, oxygen, and temperature. Future evidence must link echoes to organisms without assuming that stronger sound always means more living mass. Broadband acoustics can measure responses across many frequencies, narrowing possible body sizes and internal structures. Carefully timed net sampling can recover sturdier animals from the exact depth and moment of an observed band. Deep cameras can document fragile forms that nets destroy, while still sampling only a limited illuminated volume. Environmental DNA may reveal nearby species, but drifting genetic material cannot prove which animal produced a particular echo. Combining these records can reduce ambiguity, though no method sees the entire community without bias. Long seasonal observations are needed because a single night cannot capture breeding cycles, blooms, or changing water masses. Measurements across oxygen gradients could test whether habitat compression consistently changes migration distance and acoustic intensity. Predator tracking may reveal when scattering layers function as feeding grounds rather than merely shared depth ranges. Better physiological data could show which migrants tolerate warming and which lose access to profitable surface waters. If you return to that phantom horizon, its edges should now look less like a floor and more like behavior. The band rises because individuals respond to darkness, yet they do not move with perfect unity. Some remain deep, some stop at gradients, and others cross toward plankton, concentrated under the night sky. At dawn, the community separates again, leaving instruments to trace a descending architecture of living echoes. The strongest conclusion is measured. Early sonar detected real scattering, but sound alone could not name its sources. What once resembled an impossible seabed is best understood as changing biological layers, still incomplete in composition and consequence.